Good afternoon, everyone. My name is Kaichen Hyak, and I'm a HPC staff scientist working with UW. And today we are going to introduce the third part of our training session, which is the basics for pattern plotting. And all the materials are included in our Git repository. You should be able to find the links in the email we have sent you. And today we're going to cover basically three parts. The first one is the quick recap and continue to the NumPy library that we have mentioned during last session. And then the second one is about the, let me click on this folder. So the second one is introducing to the Pandas library, which usually used for data structure called Dataframe. And then we are going to introduce the data visualization using Matplotlib. So that will be the contents we're going to cover today. So we'll continue using the Open OnDemand provided by the supercomputing cluster Hyak clone in UW. So the link can be if you type in Hyak UW, you should be able to find the main page for our supercomputer center, and then the documentation, and then Open OnDemand in the sidebar, and start here. Then the link can be found here. Yeah. Then you may need to log in because I already logged in today. So you may the starting page may be different of yours from mine because I have logged in already. So after you have logged in to the Open OnDemand page, just click on the interactive apps on Jupyter. So before today's session, we have already added you to the resource group or account of UW-IT so that you will have access to our priority queue of UW-IT so that you won't be preempted or interrupted for your job. Yeah, so that's really upset last week. So please choose UW-IT, and the partition you can use either compute or CPU G2. And then we'll just keep this as it is. Task for 1, CPU for 1, and memory maybe we don't need 20, just 10. And then today's session is 2.5 hours, so we'll set this to 3. And click launch. So we are starting the interactive Open OnDemand job with Hyak. Please let me know if you encounter with any problem for this process. Okay, so during we waiting for the job to start, please click on the clone login button at the top of this page. Then log into the cluster. Just type in your password and then the 2-step authentication. Because we have updated the materials for our GitHub repository, so you will need to pull the latest version from the remote repository. Okay, so now we are in our home directory. If you have cloned your repository in your home directory, then you should be able to see it in your home directory. But because I haven't cloned it to my home directory, so here I don't have that repository. So I need to clone it at first. I will just copy the link. Hit clone and paste the link. You don't need to do this if you have done it last week. So change to the folder. What's the name? List. Let me see. So when you change directory CD to the to locate inside the folder, the Git repository, type in git pull. But this command will override your current directory with the latest updates. So if you have made any changes to your local repository, for example, you have created a file or modified any files inside, then we shouldn't use this directly. So if you want to keep your local, if you are okay to just override it, then you can just type in git pull. But if you don't want to do that, then you can use git stash to store your local modifications at first. Because I don't have any change, so it's okay. And then use git pull. And you should see something, it's fetching and update your local repository with the remote version. And then use git stash pop to retrieve your local modifications. So I think that should be a process that won't override your local modifications. But it doesn't make any sense for me because I already have the latest one. Okay, so after you have done so, you should be good to just exit the cluster. So just type in exit and you will terminate the remote server and close the tab. Now my job is already started. So is anyone still waiting? So for those of you that already got the job running, just click connect to Jupyter. Okay, so I'll just continue that in the left sidebar that you will find all the folders in your home directory. And we have cloned the Git repository named MEM-C REU to our home directory. So you should also find a folder, this folder in your sidebar. Yeah. And then double click it and find pattern plotting and double click it. So all the materials for today's session are here. Actually, I'm going to just do the demonstration interactively with a new Jupyter notebook instead of just run the code blocks. So this is just for you to review, and if you have anything want to come back after today's session, you can, after we conclude today's session, you can come back to all the contents we covered today at any time. So we have 3 Jupyter notebooks today, and for those starting with an S, that's just a duplicate to the main Jupyter notebook with all the solutions to exercise included. So yeah. Okay, then I'll just close it. And I would just recommend you to do this outside of the Git repository. So to start a Jupyter notebook with pattern 3. So here's the new Jupyter notebook, and I want to rename it. So right click on the tab or on the title, then you should be able to rename the notebook. I will call it pattern underscore plotting. Okay, so that's the new notebook I will be working on today. Any questions? We're fine. Yeah, okay. Then okay, so let's get started with the contents of today. And we're going to dig into the Python data science ecosystem, and it relies on a lot of third-party packages, including the one we already touched a bit last week, NumPy, and the ones that we are going to touch on today, Pandas and Matplotlib. And there are also a lot of others, such as SciPy for scientific Python. So NumPy is the library that provides an n-dimensional array that for computation and manipulation of homogeneous array-based data in Python, while the pandas we're going to cover today is mainly for tabular data, which can be heterogeneous, which means that the data type in pandas data structure can be different. That's different from the NumPy array. And Matplotlib is originated from MATLAB-based interface. And this library actually provides the capabilities for a flexible range of publication quality data visualization. So we'll start by a quick recap on the continue to NumPy library. And it's always a good practice to import the library at the beginning. So we'll just import NumPy as NP for short, and Shift Enter to run the code. The basic element for NumPy is the NumPy array. So we will start with creating an one-dimensional NumPy array. For example, we can have np.array to just create one. And the bracket, and with square bracket.
Hey, Kaichen,
Mhm.
can you do like a control plus?
Oh, sorry.
You can make it bigger. What will let you do
Mm,
man plus?
Can I just do this?
Okay.
Yeah. Okay. So we'll just type in some random numbers to create a NumPy array. So here we have 4 numbers and we have only one square bracket. So in this case, we actually create a one-dimensional array. That's very similar to Python list that we have introduced last week. If you do this without np.array, actually you can copy and paste it. What we will get is a list. So what's the difference between these two? Can anyone tell me?
One of them is inside of the break.
Mm-hmm. Yeah, so actually I think that's one thing. Another thing is that for NumPy array, you will see that even we give 1, 3, 4 some integer numbers within the array, actually it's upcast to floating point, because there is a floating point number in the array we give it. That's different from list. So the data type for anything in a list can be totally different. You can even have string. You can even have a string in the list, such as I'll just call it a word. So it can take everything. Actually, if you try to find the data type for it, you'll find it's float. Okay, so if you assign a variable for it, then try to find the type of any variable in that. You will find that it can be totally different for those of the numbers. So for example, if you have the last one, then you can have string. You have both integer, floating point, and string in the list, but that's different from what's in a NumPy array, which you only have one data type. And then next step, we want to create a multi-dimensional arrays with nested lists. So here we have similar to what we have done to create the one-dimensional array, but this time we will just use nestedness. So there will be two square brackets here, and just assign the value to be 1, 2, 3, and with comma and another square bracket, and 4, 5, 6. So if you run it, actually you will get two rows and 3 columns. That's created by nested list assign those values to the array. The inner list, so the inner square brackets are treated as rows of the resulting two-dimensional array. So in this case, we got the two-dimensional array. And as I showed before, that we can use the dtype attribute to get the data type of the NumPy array. For example, we can assign a name to it to be x2, and this one to be x1, so that we can retrieve those arrays later just with the variable name and run them again. And then it can be just called by the object x2, the variable, and then with the attribute or the variable dtype. And it will show us that because here we only have integer values in our array, so they will infer the data type from our input, and this time it's just integer. There are also some other useful attributes from NumPy array, such as if we want to try to find the dimension of the array, so we can use ND. That's for the n-dimensional. So in this case, we can find that our array is a two-dimensional array. And also, if we want to find the shape of our array, how many rows and columns are there, we can use the attribute shape. So we have 2 rows and 3 columns for our x2 array. And you will find that actually here you are getting 2 numbers. So that's a tuple of the, it returns the tuple of values. So sometimes we want to only get the row. We want to use the number of row or number of columns in our later codes. Then you can get that just by using a square bracket with 0 for the number of for the first number, which is the number of rows, or 1 for the second number, which is the number of columns. So that's something interesting to play with. And if you want to know how many elements are there in total, then you can use the variable size. So it will tell you that we have 6 numbers in our NumPy array. So that's just some useful attributes from NumPy array. And here we just create every arrays manually, but sometimes we just want to create an array with a certain dimension, such as 6 by 5, but we don't need to know the value of each element at the beginning. So we just want to assign a particular shape of an array. So in that case, we can just initialize an array with NP zeros, which will fill the array with zeros. And if it's just a one-dimensional array, then you only need to give it one number here, so it will give you an array, a one-dimensional array with 10 zeros. By default, it will be initialized to a floating point number. So if you want to have integers, you can specify the D type equals to int. So in that case, you will just have integers. And if you want to get a two-dimensional array, so instead of giving just one number, you will need to give a tuple, just as you have got with the dot shape attribute. So you will give it. So if you want to have a 3x4 array, then just give it a tuple of 3 and 4. So there are similar methods. So here we use zeros, and you can also use ones to fill them all with 1. And if you want to use any random number or any other numbers, you can use the function of foo and tell it what number you want it to fill with. Oh, I use the type equals to int, so it's downcast. Yeah. So here are just some simple methods to create arrays from scratch. When we do plotting or any other coding, we often want to get a list of numbers or an array of numbers that with equal space between them, with equal step, or we know that we have a start point and end point. We want how many numbers between that range. So there are two functions to achieve these two goals. The first one is the np.arrange. This is very similar to the range function we have introduced in the conditional statement, the if-else statement, that you can get. So for example, 5, then you will get that will just give you the range, but you can always iterate from 0 to 5 with the range function. But here for NumPy.arrange, you will get linear sequence with this function. And for example, we can specify 0 to 5, and you will get an array from 0 from the starting point, and the end point is exclusive, so it will end at 4. In this case, because we didn't give it a step, so it will use 1 by default. If you want a step such as 2, then the step can be 2. And if we only know the starting point, the range, and how many numbers, we don't know the step, then we can use a function called linear space, lin space. And so for example, 0, 5, we want 10 numbers between. So that's what you will get. So between 0 and 5, in total, you have 10 numbers. So the difference here is that for np.range, the end is exclusive, while for the lin space, the end is included. So there will be a subtle difference between those two functions about how they handling the endpoint. And right now we have created or defined arrays from scratch. And if we already have an n-dimensional array and we want to reshape it, then we can use the function called reshape. So for example, we can take advantage of the arrange function to have numbers between 1 to 12, 1 to 12 through 12, stepped by 1. And now it's just a one-dimensional array, but we can reshape it to such as 3 by 4. Then in this case, you will see 3 rows and 4 columns, and the orders are from upper left to bottom right. So the exercise now for you is to use linked space to do the same things. And one hint is that here for linked space, it will use floating point number if you don't specifically tell it to use integer. So if you want to have an array of multi-dimensional with all integers, then you may need to also specify the data type when you create it with linked space. Okay, so I will just try to do the same thing. And I just want to assign a variable to it. We call it x3. And if we want to use linked space, then we need to specify the starting point and the end point. And for linked space, the endpoint is included. So here we only need to use 12. And we have 12 numbers in between. And we want the data type to be integer. And then reshape it to 3, 4, to 3 by 4. And if we print it, we can get exactly the same thing. And you can always reshape it. For example, we can reshape it to 2 by 6. Then you will get 2 rows and 6 columns. So there are a lot of things you can do with it. And after we got an array, I think the first thing we may need to figure out is how to select a specific element in the array. So for example, if we have x3 here, we already have a 2-dimensional array with 3 rows and 4 columns. Then what if we want to get number 7? So we may need to use the indexing with a square bracket, and then the indexing for array, just as you roll the pattern the pattern that the indexing starting from 0. So this is the 0th row on the first row, and then 0th column, first column, second column. So with this index, we will get 7. And it tells you that the data type of it. If you don't want it, you can use print. Then yeah, you will get 7. So that's how we select a single element in an array. And after you select it, you can also modify the values using this index notation. So for example, we have select the x. And then you can assign another value such as 3.14 to it. and print x3. The interesting thing here is that because NumPy array have a fixed data type. So if you attempt to insert a floating point value to an integer array, the value will be truncated. So that's what's happening here. Instead of 3.14, you only get 3. And if we want to select multiple rows or multiple columns or both, then we can it's very similar to the pattern list that we can use the colon character. So for example, if we want 0 to 3 and 1 to 4, the 0th to 3rd rows and the first to 4th columns, we just separate them by the colon character. And then we will get a sub-array from our initial array. And the lower and upper limit they are optional. If you don't specify it, it will use 0 for the lower limit and the highest number of the volume as of the column for the upper limit by default. And if you want to select with a step, then you can use another column with the step you want. Yeah. So the general format for this is the variable for the array object, and then the start point, and stop, and step. If you use the colon character by standing alone, then you will then you will just get the entire rows and entire columns. And one important and extremely useful thing to know about array slices is that they return views rather than just copy the array data. And this is a NumPy array, where NumPy array different from the pattern list. So for example, we have a subset. We assign a subset of x3 to the variable, a new variable called x3 sub, and we just select part of the original data set. So we can examine this is the subset of the array, and then if we assign one element in it, for example, just the first element to be 99, and then if you print x3 again, you will find the original array it's also changed. So that's an important feature for NumPy array, that if you modify the element in a sub array, then the original one will also be changed, because the array is not copied to the new variable. So if you want to sometimes we may don't want this happen, that we may not want this happen, that we only want to change the new variable instead of the original array, then you can use a function called copy to copy the original array to a new array instead of just replace it, or just, yeah. Okay, so that's all for the NumPy part. Any questions?
you just take the individual values and you put them in a single, say, vector or a single list without it being connected to.
You can. So for example, if you want to assign, you want to put a single value from the original array, then I think you should use the copy function instead of just direct assign the value. Yeah. Yeah, you can do it just by using the copy method. I just maybe, yeah, in this way I'm sorry, so it should be. In this way, you get A equals to the first element in X3. And if you assign a new value to it, for example, 0, and in this case, the original array won't be changed because you just copy it to the new variable instead of connecting it to the original one. Yeah. So you can always do this for not only the single element, but also a sub-array. Okay. Okay, so if no more questions for NumPy, we will continue with the Pandas data frame. Okay, so we can continue in this notebook, or if you want, you can also start a new one. And Pandas is actually a newer package that built on top of NumPy array, and it means that the most methods or functions we introduce here for NumPy also applies to the Pandas data frame. And the data structure in Pandas, it provides an effective implementation of a data structure called data frame. And the data frame is a collection of columns, of labeled columns. And those labeled columns are called series in Pandas. The data frame actually is the way that Pandas used to represent a table, and series is the data structure Pandas used to represent a column. And so first of all, we'll just import Pandas as PD for short. If you are interested in Pandas, then you can use the help function to Oh, okay. I think it's it. Oh, okay. Yeah, to see your short documentation for Pandas. You can also find a more detailed one online from the Pandas website. The first step today is to read in the So yeah. So the data set today, the data set we are going to use today is it's just a very plain text, or the data separated by comma provided online for periodic table. So there are the numbers and strings here. And you can see, if you look into the first line, you can see something like atomic number, element, symbol. Actually, those are the first line is just the header for each column. So we will call them as the label for each column. It's hard for us to just directly read them in this plain text. And we can, I have the data file is provided actually in the in our Git repository, pattern plotting, data. Yeah. So in this case, if we want to read in the data from the data file we provided, we can use the function read CSV. CSV stands for comma separated values. And we will assign the variable called periodic table to it, and then use the function for pandas, which is shortened as PD, read CSV. And the argument it take here is the full name, including the path to the file. So here we have it depends on where you are working with this current notebook. So if you are doing something like me, that you are just create a new notebook. Let me see where to. Oh yeah.
Thank you.
Read underscore CSV with bracket. So before we run this command, we need to give it the keyword of the file name. So file name is periodic table. If you just do this, then actually we will encounter with an error telling us that the name periodic table is not defined. That's because our current notebook is not in the same directory as the data file. So it will not be able to know where the file is. So in this way, we need to type in the full path to the data file. So for here, my the working directory for my current notebook is my home directory, and then I will go to MEM-C REU at first. So you will need to type in MEM-C -REU / and if you double click on MEM-C -REU, and then it's in the pattern plotting folder. So you will also need to type in pattern plotting and then / and it's in the data folder. So data / oh, I'm sorry. So I think you also need to make this as a string. Let me examine it. It's CSV. Yeah, it's CSV. Here is a typo for me. Yeah, so in this case, we have reading the data to a pandas data frame named as periodic table. So if we view the data frame, you will see something like this. So here my file name looks like this because that's my file structure. So in your case, it may be different if you put your current notebook in a different folder. So if you just open the Jupyter notebook provided for data frame, you will find a simple explanation for the file structure here. That for the notebook we provided, it's under the pattern plotting folder, and the periodic table is under the data folder in the pattern plotting. So you will need to provide the full path for the file, for the data file that we are going to work with. So any questions, or do you have the data? Okay. Another way to do this is because here we have the data online, so actually you can just, if that's the case for your own data, then you can also use the pd.read CSV and with quote, and then just copy the link of your own data. So for here, we have the link here, and then if we copy and paste it, you will also be able to get the same thing. If your data is online, then the file name can also be a link to the data. So here we have the data file locally, so you will need to give the full path of the data file. So you may have noticed that by default, it will take the first line as the label for each column. But for each row, actually it automatically generates integers starting from 0 to index each row. If you want to assign one of those columns as the index for each row, then you can do so by when you read in the data. So for example, you can define the index column equals to element. Then you will see that the column of elements are set as the index for each row if you do this when you're reading the data. Okay, I don't want to do this right now, so I will just revert it. And so with this overview for our data frame, actually we can find that the Pandas data frames actually they are good for tabular data, and here usually the columns are the observed variables and the rows are the observations. So we have a lot of different properties for each element, and each element, each element is stored in one row, starting from the hydrogen to the end of the periodic table. And we can also use shape to find out the shape of data frame, such as periodic table dot shape. It will tell us that there is 118 rows with 28 columns. And sometimes we may want to reverse the rows and columns to treat columns and rows and vice versa. And we can use the T attribute stands for transpose. And then in that case, we can view the rows which are originally the columns, and the columns are originally the rows. But transpose doesn't copy the data, so it just changes how we view the data. So if you run print periodic table again, it will back to the original format. Two useful functions to get first impression of the data is to use the head and tail function. So for example, head will display the first 5 rows of the data by default, and tail will display the last 5 rows by default. If you want to change the number of rows to be displayed, you can tell it. So if you want the first 10, you can just specify the number of rows you want it to display. And sometimes we may want to display, for example, the last 3 columns instead of rows. In that case, we can use T for transpose at first, and then use tail 3 to display the last 3 columns of the data. So dot T to transpose it at first, and then dot tail 3 to display the last 3 rows. But as we already transpose it, so that will be the last 3 columns. And sometimes there are too many columns here, so actually some of them will be abbreviated, so we won't be able to know what's the label for the columns. So, and a useful way is to use the variable columns. This will print all the column index or the column label of this data frame. So we will have in total 28 columns, with each of them has its own label, starting from atomic number, element, symbol, to number of shells, number of valence. And if you want to find out the label for each row, then very similar, just use the attribute index. So this time, because we haven't set the index for the table, so actually it automatically generates the integer from 0 to the number of rows set as the row index. So you will see that it's just a range, start from 0, stop at 118, and step is 1. So if we set the index for our data frame using as element, and we want to set in place, which means replace the original data frame, and also set it to true. And we don't want to drop the column. If you don't set drop equals to false, then the column set as index will be dropped from the table. Then if we take a look at it, we have element as index, and the element column are still there, is still there. And then in this case, if we run the periodic table dot index, it will show you all the elements for each row. Any questions? Okay, I'll just continue. And then as what we have done for NumPy array, for Pandas data frame, there's also a lot of occasions that we want to select a single value or slicing the data frame from the original one. Then actually Pandas provide two functions, the data frame dot iloc and data frame dot loc for accessing the data. Alloc stands for the integer indexing, and loc is stands for the label-based indexing. So we will introduce these two functions here now. And so for example, we have periodic table, and if we use alloc with square bracket, and then type in 0, 2, and run it, you will get H. So what that means, it's the two numbers, it's very similar to the NumPy array indexing. So the first one is the number of row. So here is the 0th row, so it's the hydrogen, the row of the hydrogen. And then the second column, the 0th first second column, so it's the symbol for hydrogen. That's why we get H. So that's the entry we are selecting. And this can be achieved also by loc. And in this case, we need to give the label for each row, for the row and column. Here we know that the label for the row is hydrogen. So type the string hydrogen. And then the label for the column, which is the symbol. So you will get exactly the same result. These are just two different ways to indexing the data frame. As we mentioned at the beginning, that data frame is just a connection of series, which is the column. So actually there is also, if you want to select the single column, there is an attribute style way to do this. For example, if we want the column of symbol, then you can just use the data frame dot periodic table dot symbol. So in this way, you will actually, it will return the series or the column of symbol. And this is equivalent to get the column by using the dictionary way. And if we want to get multiple columns, then here we will need a nested index as using two square brackets separated by such as comma. If we want symbol and atomic number, say. then you will get 2 columns. So that's the most convenient way to select multiple columns, I think. So please be aware that you will need the double square bracket. I think we will use this a lot to when we do the plotting to get the subset of the data. And actually this can also be done by the log and alloc function. So for example, we can use alloc to get the first 5 rows, or similarly use log to get rows from hydrogen to carbon. The interesting thing here is that for alloc, if you specify the indexing from 0 to 5, the endpoint is exclusive. So the carbon will not be included. While for log, when you specifying hydrogen to carbon, carbon will be included. So that's a major difference for the alloc and log function. And if we want to slice both the rows and columns, then just add comma and the column numbers such as 1, 2, 3. So it will slice both the columns and the rows and columns. The similar thing can also be done for log. Yeah. Yeah. But for the if you're slicing with you just separate them with a comma, then I think the order doesn't matter. So yeah, the 2 ways are very similar, except how they handle the endpoint. So I believe that's also something we mentioned previously, that different methods may handle the endpoint differently. Any questions? Yeah.
Like a recap, like a very good
Mm-hmm.
It was the one that, like, it was able to kind of do the H, yeah. Could you explain that one again? Line 85, like.
Oh, this one.
Yeah, so it's like multiple.
Yeah. So for log, it takes the label for each row, for the row and column you want. So here, if you want to select the same element, the same, I should not use the same entry as ilog, then for the 0th row, here the index for the row is the hydrogen. So that's why we specify hydrogen at first, and then the row, the label for the row. So here is the second the column. So here is the second column. So the 0th, 1st, 2nd. Then the label for the column is symbol. So we use symbol for the first index or for the second index. Okay, so you have hydrogen and axis and symbol, and then it will get this entry.
Oh,
Yeah, so it's very like x and y axis. So
I thought.
that's how you locate it. Yeah. And we always give the row index at first and then the column index. And I think that's how pattern consider the axis, that the row is axis 0 and the column is axis 1. Yeah. So that will be used a lot when you want to apply some operations along a certain axis. Yeah. Okay, so let's just continue. And I think another more about 20 minutes, then we can take a break. And for Pandas data frame, if we sometimes we also want to select, instead of knowing what element or the specific entries we want to select, sometimes we just want to apply a condition to it to select those entries that fit the condition, just as what we have done with the if-else statement. So for example, if we have a periodic table and we want to select those with atomic mass smaller than 10. So if you run this command, you will get a column that's with Boolean values. And you will see some truths and a lot of false. So actually this is we call it a masking operation, that it will apply this condition to each entry, and if the value is smaller than 10, it will return true. If the value is equal to or larger than 10, it will return false. And then in the end, we will get a Boolean, or we call it a Boolean mask with true and false. So if we apply this mask to our data, so for example, we have periodic table, and we can just apply this mask, copy it within the bracket, the square bracket. We will get only those rows with atomic mass smaller than 10. So that's a very useful function. And this Boolean mask or this condition can be as complicated as you want. So for example, if we want to have two conditions, the first one is atomic mass smaller than 10, and we code them with brackets. And then we also want another condition, such as the periodic table density, maybe. And we want it to be, say, larger than maybe 1. Then you will get only one element, only one row that fit both conditions. So what's inside the square bracket is the conditions that we want to filter the data. And they can be connected by those conditionals, such as here is end. So we want the data to be filtered to fit both of the conditions. And it can be different logic statement. So one question for you, that how to get data with melting points higher than the boiling point. So we all know that usually for any material that the boiling point will be lower than the melting point. But is there any element has a reverse relationship? If you want to retrieve what's the exact label for the melting point and boiling point, please remember to use the dot column function. So here we have melting point without space and boiling point. I will also try to answer it myself. And we have a periodic table and square bracket. And we want to put the condition here. Then I think the condition will be the periodic table square bracket and quote melting point higher, which is larger than the boiling point. Yeah, that's amazing. We have 3 elements which have a higher melting point than boiling point, and we can just filter them with this simple condition. Any questions? Okay, so let's just continue. Then we have done a lot of things to the data in data frame, a Pandas data frame. If we examine the data, actually you will find that there are some entry with NaN values. That's the how pattern show a missing value for the entry. Generally, pattern handle missing values in 2 forms. One is called, sometimes you will see there is an entry with long, which means it's a pathonic missing data, but it cannot be it cannot be operated by any mathematic operations. So for example, if we have NumPy, we have a NumPy array with 1, 2, 3. Let's assign it as example 1. And a second array with this non-object, which is also a missing value. Then if we apply any mathematical operations, such as, should be 2. I want to have different names for them. If we apply any mathematical operations, such as add 5 to the array, this operation will be applied element-wise. So you will have an array with 5 added to each element. But if we apply this to the one with a missing value shown as none, then you will get an error because none is an object, so we cannot apply mathematical operations to it. A different type of missing value is the NaN, which is an abbreviation for not a number, I think. So if we have example 3 equals to NumPy array want to type missing data, and if we apply the same mathematical operation plus 5, then actually it works. So instead besides you still have empty or a missing value as the third entry, but you can apply mathematical operation to this kind of missing data. So Pandas actually is built to handle those two types of missing data almost interchangeably, I think. And we can use a function called isNA for Pandas data frame to find the missing data in a Pandas data frame. So most of them are just false, but you will see there are some truths in the Panda in the data frame, which means those values are missing data. And our useful way to get more information of this is apply an aggregate to it. For example, sum. Then you will see the statistics of how many missing values are there within each column. So for the first several columns, we don't have missing value, but for group, we have 28 missing value. That's understandable if you imagine the periodic table, because I think there are some rare earth elements that we don't assign a group to it. So that's a useful way to analyze the data. If we want to check the missing value along a different axis, here it's summarizing the missing value along each row. So if we want to apply this to sum it over columns, then we need to specify it as axis as 1. Then we will get how many missing values are there for each element. Yeah, so just apply the operations along different axes. By default, its axis equals to 0. And so to handle those missing data, if that's a pre-process for our data, if we want to do data visualization or data analyzing the data, analysis. So we can use the drop NA function to drop rows with missing value, but we got empty data frame because drop NA will drop the entire row if there is a missing data. And if we check our statistics, actually every row has a missing data, at least one missing data. So all rows are dropped. That's not what we want. And one way is so if we only want to drop the columns with missing data, because there are some, as we have seen previously, that there are some columns that are full without missing data, then we can specify the axis to be axis equals to 1. And it only drops 18 columns, I believe. Originally, we have 28 columns. Now it dropped 18 columns. And if we still want to drop the entire rows, but only for the rows that have missing data in a specific column, So then in that case, we need to use an argument called subset. So for example, if we only want to drop rows with missing data in density, then only part of only a small proportion of the data will be dropped. And if you see at the lower left corner, then it dropped only 13 rows. That's very that's exactly what we see for the missing data in density, that we see there are 13 missing value in density. So if we drop those rows, then we will have 13 less rows after we dropping the NA data. And so one exercise for you is to drop rows with non-metal elements and print only the group and non-metal columns. So here we use the drop NA function, and we only want to drop the rows with missing value in non-metal. So we use this to drop those ones. And then there are a lot of columns here. We don't like it. We only want the group and non-metal columns. Then we can use what we have introduced in this session. The simplest way to select a subset of the columns is to use the dictionary nested lists. So we only want to select group and non-metal. So so then we will have a much cleaner and simpler data frame, or the table that only showing us with the group number of the elements and the non-metal column. Now we already dropped all rows with missing value in the non-metal columns, so you will find that every rows here, they have a value for the non-metal column. So those elements are considered as non-metal in the periodic table. Okay, so that's all for Pandas data frame. So we have introduced how to read in data from an existing data set, either from the internet or from a local data file, and then the basic attributes to get the basic dimensional or the label information from the data frame, and also the how to select a single data and slicing a portion of the data, and then the manipulation of the data. Oh, there is the last part to cover is if we want to create a new column from the existing data, then actually it can be done really simple. Just periodic table, assign a name, what we want to call it, for example, call, and it equals to the periodic table for core electrons. It should, or no, it's for core, we want it to equal the number of neutrons at the number of protons. Yeah. Let me see. What is the number of protons? Okay, so in this way, if we print the periodic table again, we will find now we have 29 columns, and the column of core we defined will appear at the end of the table. So that's a very straightforward way to add a new column based on the existing data. If we have two data sets and we want to combine them, then the method we can use is called the concat, stands for the concatenation of the data. So we can define two data sets. Let's define them as with the subset of the data. So for example, D1 equals to periodic table dot ilog. Maybe 0 to 2 and 0 to 2. So that's what D1 looks like. And then D2 equals to periodic table alloc 3 to 4 and also 0 to 2. Oh, sorry, I want to use 2 lines, so 0 to 5. So here we have a slice of the data, and if we want to combine them two, and then we can use the concat function. So let's use pd dot concat bracket on square bracket with df1 and df2, d2, d1, d2, and axis equals to 0. So those two data sets will be combined along the zeros axis. So that's along the row. So that's what we will get. We can also use concat along the axis 1. Then it will along the y-axis, the column. So the interesting here is that if the labels are the same, then it will merge them in the same column or rows. But if the labels are different, then because here we specified explicitly to have the two along the column, so that's why you saw a lot of missing values. But if we define D3 with different column index, say 1, 2, 3, then if we concact D1 and D3, then you will see that it will merge the common columns. Both of them has the element, a row called element for both D1 and D3 here. But D1 has another column called atomic number, while D3 has another column called symbol. So if you concatenate them, then the common column of element will merge, while the distinct columns will remain as original. So the empty entries will be filled with missing values. So that's how it deals with concatenate. And we already used sum, the aggregate operation sum, in the above notebook. There are a lot of other aggregations in for both NumPy and Pandas. So for example, they have maybe density. Then you can also use, we already tried some. And then you can also find minimum and maximum value, use min and max. And actually there is, in addition to those common aggregates, Pandas also provide a convenient method called describe. We'll show you we'll compute several common aggregates for each column and returns the results. For example, the count for each column and the mean value, the standard deviation, the minimum value, value below 25%, 50%, 75%, and the maximum value. So describe is just a convenient way to have a basic information for the data in the data frame. And so for periodic table, naturally, actually, as we have learned, we have different groups and families for the periodic table. So that's also the case for a lot of data sets that we will be dealing with. And we can always group our data by the labels. So for example, that we can use group by for group based on their families or groups. Oh, sorry. So we also need to give it an aggregate. Oh, you will need bracket. Yeah, so in this case, we will group the data based on their group and then count how many entries are in each group. So that's so the general process is the first step is to split the original data by the condition we gave it. So here is the group. Use group by and then apply the congregate, such as here we use count. And then the last step is to combine the results for each split and then combine them in the final results. So it's very interesting if we look into the table here that we see elements of six or seven elements for some of the row of the groups. So if you count it, you will find there are in total 8 groups. That's what we call the main group. If there's only 4 elements in that group, then that's the side group, I believe. So that's what we call those groups. And so besides the group, we can also group the data by period. So for example, use periodic table dot group by bracket with square bracket and period, and also count. Oh, sorry. And then it will count how many elements are there for each period. So you can do a lot of things for this data, such as if you want to compute the mean value for each group for their density, maybe then you can just group them by period and then subtract the density column and then apply the aggregate operation mean value to it, and then it will calculate the mean value of density for each group, or for each period, sorry. So that's just some things that we can do to pre-process or manipulate the data set we have. Actually, we didn't touch much of the keywords that can be used when we're reading the data. You can also specify the number of rows you want to skip, or the number of rows that you want to use as the header. So yeah, so that there's a lot of things that you can control. And actually, if you want, you can find all of those things in the documentation. Yeah, so if you type read CSV, click on the Pandas documentation, you will see all the keywords that it will take and a detailed description in the parameters. So yeah, so for example, you can specify the delimiter and the header, the row number that's containing the column labels, and also this is for you to set the index label. So there are a lot of parameters you can use. Also how many rows you want to skip, you skip rows. So for all of the functions we introduced in our training session, you can always find a documentation like this telling you what parameters it will take. Actually, if you are coding with VS Code or Cursor, a lot of the packages that nowadays they incorporate AI into it, then when you type in a bracket and your cursor in between, it will automatically, there will be a floating window, I believe, that automatically show you what keyword it will take. Yeah. But the problem is that when you have really heavy coding or process with a large amount of data, then you may need to use a cluster for it to run, because our own computer sometimes may not be able to run a very large data set. Also, that's what we are doing with OnDemand. That's actually all of those codes are not running on our own computer. Our own computer is just a monitor or a screen that's showing us the results, and the real process is happening at the back end on our cluster, a high performance computing cluster. So yeah, that's what we use the HPC for. If you have a very memory heavy or computation heavy work to be done, then we can utilize the resource from HPC.